Good question, but let me explain. So the question is that xx equals to 0. Very strange. X times x is 0. The property was as follows. X is 0 if and only if x equals to 0. That is the property, right? Look at your lecture. Yeah, so I wonder if it was written like that. No. So it was written x less or equal than 0 and that one. These are two properties of an inner product. Yeah, okay. So I was afraid that I made a mistake. Okay, so let's continue. And I decided to change the principle of numerating. So sections and chapters are huge logical pieces of our material. Okay, chapters and sections, and each lecture maybe it contains several logical pieces, doesn't matter. So each lecture is a separate story. And last year I tried to make enumerating of every section according to lectures, right? This year I'll not do it. I didn't like that practice, in fact. So I prefer to preserve chapters and sections just for logical material. And lectures, okay, you have also your video recording, right? There are numbers of lectures, and that's it. I don't want to make extra numerating because of lectures. Okay, so it means that we still continue very long first section about spaces Rn, and during last lecture there was a long series of lemmas, and now we start with theorems. So Theorem One. So numerating of theorems and lemmas and so on will be just for each lecture, because otherwise you will forget, I will forget, and so on, right? So don't worry about numerating of theorems. Just for every lecture we start from the beginning, okay? Because you can easily find numbers of lectures. That is essentially easier, right? Okay, so Theorem 1 is about interior and closure from the point of view of open set. So for every set E in a metric space X, in a metric space interior E is an open set and closure of E is a closed set. Okay, so proof. First assertion, interior is open. So what we want to prove? Take arbitrary point in the interior, right? If it is empty, then it is open automatically, we know, right? So what it means by definition? By definition, it means that there exists a number epsilon greater than 0 such that a neighborhood of the point x0, epsilon neighborhood, is in E. Now, I'll use lemma with number 2, I think, from former lecture. It was lemma, yeah, lemma 2 from former lecture. Lemma 2 of lecture 2. Lemma 2 of lecture 2, which says that if E1 is a subset of E2, then interior of E1 is a subset of interior of E2. That was in lemma 2 during last lecture, right? So it means what we can deduce. So we have a set E1, set E2. Hence, according to that lemma, we obtain interior of U epsilon of x0 is a subset of the interior of E. But interior of an open set coincides with the set itself. And we know from another lemma with number 3, lemma 3 of the same lecture 2, says that every open ball is an open set. Hence, we deduce that this interior coincides with the open ball itself. And now look what we obtained. So, for arbitrary point x0 in our interior, there exists epsilon such that epsilon neighborhood is in this interior. And it means by definition that interior is open. That's it. So that is the first part, just using a couple of lemmas. Second part. So we want to prove that closure is a closed set. So what it means, a closed set? We want to prove that arbitrary adherent point of closure E belongs to this closure. So the closure contains all adherent points. So then take arbitrary adherent point. Let it be x naught. Arbitrary adherent point of closure. What it means, adherent point of a closure? It means that, so by definition, what means adherent point? For arbitrary epsilon greater than 0, the intersection of epsilon neighborhood with our closure is not empty. And if a set is not empty, it means there exists something inside. So there exists a point. I'll denote it x1. Of course, it depends on epsilon. For every epsilon, it might be different, right? And there exists a point x1 of epsilon such that it belongs to this intersection. So it is in the closure and simultaneously in our neighborhood. And I wrote firstly closure. Why? Because now I want to use this. So what means x1 is a point of closure? Closure consists of all adherent points of E. So it means that in particular x1 of epsilon is an adherent point of E. So you see, x0 was an adherent point of closure, and x1 is an adherent point of the set E itself. Okay, again, what it means by definition? By definition, it means that maybe, by the way, maybe I took epsilon over 2 here. Epsilon over 2 here. Definitely it doesn't matter at the moment, right? Arbitrary epsilon over 2, it's not important. So, x1 is adherent point. Once again, for this epsilon, now epsilon is taken and fixed. We took it. And after that, what happens? We again use the definition. So the intersection of epsilon over 2 neighborhood of our point x1 of epsilon with the set E is not empty. So what it means? It means there exists a point x2 of epsilon, let it be, which belongs to this intersection. So one thing is this is in E. That's important. Another thing, let's compute the distance from x0 to x2 of epsilon. According to the triangle inequality, we can insert x1 of epsilon. And now look, x1 of epsilon was a point in epsilon over 2 neighborhood of x naught, right? It means by definition this distance is strictly less than epsilon over 2, right? And here, once again, x2 of epsilon belongs to epsilon over 2 neighborhood of x1 of epsilon. So it means the distance is again less than epsilon over 2. And that is epsilon. And what it means? It means those things together. It means that the intersection of epsilon neighborhood of x naught with E is not empty because it contains point x2 of epsilon, right? And we did it for arbitrary epsilon greater than 0, right? So for arbitrary epsilon greater than 0, we proved that one. And it means indeed that x naught belongs to the closure of E. That is an adherent point of E. So the theorem is proved completely. Okay, now lemma. Let it be lemma 1, new numeration. Yeah? Here it is written x naught is arbitrary adherent point of closure. Yeah, we want to prove that adherent point belongs to closure. So x naught is not a point of closure from the beginning. We don't know. That is adherent point of closure. So you have an operation, closure, right? You make, in general, set greater than it was before. So the question is, maybe we can continue. We can make closure of closure, but it makes no sense because closure is closed set. So closure of closure, no sense. It's just maybe that is good to mention as a corollary. So corollary, closure of closure is just closure. So, and same for interior also. Interior of interior is interior. So makes no sense to use those operations twice, or that is idempotent property of those operations if you prefer algebraic language. Okay. So lemma 1, yeah, that is a kind of duality between those operations. So for arbitrary E in X, I'll not use words. So once again, we have a metric space. Everything is the same. We have X minus interior E is equal to closure of X minus E. And X minus closure of E is interior of X minus E. So duality between those operations takes place. Proof. So let's start with this equality, first equality, and in fact I'll prove firstly one inclusion and then another. So take arbitrary point in the set which is written in the left hand side. So what it means? X naught belongs to the difference between two sets, right? It means that X naught is a point of x which is not included into interior, right? What means not included into interior? Interior contains all inner points. Is not a point of interior means is not an inner point. Let me recall where is, you see, definition of inner point is here. There exists epsilon such that neighborhood is in E, right? So that is not true. What it means for arbitrary epsilon greater than 0. Okay, now what means one set is not a subset of another? What it means? Not true. So, not true. Right? That is not true. What it means? A is not a subset of B. It means that the intersection of A with complement of B is not empty, right? So it means that U epsilon of x naught intersection with complement, it means x minus E, right, is not empty. So not a point of interior, right? Okay, now look what is written. That is precisely the definition of adherent. So x naught is an adherent point of this set. Precisely. Look at the definition of adherent point. Here it is. Yeah. With epsilon over 2 doesn't matter. So for arbitrary epsilon, neighborhood intersected with this set is not empty. So it means that x naught is a point of closure of this difference. But now you can repeat this chain in inverse order. Look, once again, x naught is a point of closure. It means this is adherent point of that one. So it means for arbitrary epsilon, this neighborhood intersected with that difference is not empty. It means this neighborhood is not a subset of that set, right? Is not a subset of E, so x naught does not belong to the interior. So in fact, you can proceed in inverse direction as well. And it means we have equality of two sets. We have equality of two sets. Okay, now second part. It's quite analogous. So take arbitrary point in x minus closure. Once again, what it means. X naught is not an adherent point. So to be adherent point, we need this one. For arbitrary epsilon, neighborhood intersected with E is not empty with E. If this is not true, we should put here there exists epsilon, right? And converse assertion equals to empty set, right? So it means U epsilon of x naught intersected with E is empty. Is empty. So I took the definition of adherent point and take negation of this definition, right? Now what is written here? A set intersected with E is empty. It means that this set is a subset of complement. What is complement? Everything else, right? So this set is subset of complement. So let me recall. There exists epsilon greater than 0 such that this neighborhood is inside x minus e in the complement. But look, if there exists a neighborhood in a set, then it means that x naught is a point of the interior of that set. Right? And now, once again, we can proceed in inverse direction as well. Look, if x naught is a point of interior, then it means there exists epsilon such that a neighborhood is in this set, right? It means that the intersection with E is empty, and it means x naught is not an adherent point of E. So, once again, we have equivalence everywhere, and it means we have equality here. Equality here. Okay. And now, Theorem 2, quite important theorem, although we don't need to prove now. Theorem 2. E is an open set if and only if x minus e is a closed set. So why I don't need to prove anything? So if E is open, it means interior coincides with E. That is by practically by definition, right? Or you may refer to Lemma 1. So open set means E open equivalent interior equals to E. So follows from, or maybe I wrote it as a corollary. Did I write it? Yeah, it was a corollary of Lemma 1. Corollary of Lemma 1, lecture 2. Lecture 2. And look, so it means now x minus interior equals to x minus e, right? But as we know by lemma, that is closure of x minus e. And once again, x minus e is closed if and only if closure of this x minus e coincides with x minus e. And that is same corollary. Same corollary. So that's it. That's it. Okay, now one more definition is exterior. So maybe definition. An exterior point of E is an interior point of x minus E. So exterior is a point in the point of the complement. And the set of all exterior points of E is denoted by exterior exterior. Okay, so next is boundary point definition. Boundary point of E is neither inner nor exterior point of E. So boundary means you are not in interior and not in exterior. Between interior and exterior, right? Okay, so and maybe let me write it like a lemma. The set of all boundary points of E is denoted by this one. E, sorry, E, partial E. That is boundary, or shortly, just boundary of E, without point, boundary of E. Set of all. How the existence of boundary point possible is either in or exterior. Yeah, let me give an example. Example. E is such a set. Let me consider 1, 3 together with let it be 4, 5 intersected with rational numbers together with 6. So we consider everything in metric space which we considered before, the set of all real numbers, right? So let me make a picture. 1 is not included, right? We have 3 is included. Then 4 is included. 5 is included. But you see, I'll indicate it like that, right? Only rational numbers here are taken, right? It's impossible to make a picture precisely. And also we have 0.6. That is our set, right? So look, what is interior? Look here. at the interval 1, 3. Every point of that interval, open interval, without ends, right? Every point inside belongs to our set with a neighborhood, right? You can find small neighborhood which is inside our set, right? It means that interior is 1, 3. And nothing else. Why? Because if you take arbitrary rational number, right, doesn't matter how small neighborhood of this rational number you take. There are irrational in that neighborhood, right? So it means this neighborhood does not belong to our set E. So no more inner points. What are exterior points? So everything what is less than 1, right? Also, look, from 3 to 4, but also only inner point, right? Because what is exterior? If you put here and take here a point, you can find a neighborhood which is in the outside of E, right? Which does not intersect with E. You can do it for 3, 4, but you cannot do it for irrational points of 4, 5, right? Because if you take arbitrary irrational number, in arbitrary neighborhood of this irrational number, there are rational numbers, points of E. Also, you can take 5, 6, and 6 to infinity. So, boundary 1, 3, and the whole interval from 4 to 5 and 6. So every point of this interval from 4 to 5 is a boundary point, right? Because it is neither in exterior nor in interior. That's it. Okay. Let's have a break. Last lemma in this section, and that is, let me formulate it with, yeah, in fact that is second lemma, right? So lemma 2, so yeah, let me formulate like that. First, x belongs to the boundary if and only if x belongs to closure minus interior. Second, x belongs to the boundary if and only if for arbitrary epsilon greater than 0, the intersection with E is not empty and the intersection with complement is not empty as well. So that is, in fact, each of those assertions, I mean not assertions, but just look at right hand side, right? These are alternate definitions of the boundary. So sometimes boundary is defined like that, sometimes just by this property. So in arbitrary neighborhood you have both points of the sets E itself and of its complement. And concerning the proof, okay, look at the first one and compare with proof. No, with definition, sorry. So, neither inner nor exterior. Not inner, it is written here, right? Not exterior, look. So, if, look at this one. Where is it? Yeah. So, complement. So, what is exterior? Exterior is here. That is exterior, right? Because what is exterior? Interior of a complement. So, if it is not an exterior, it means where is it? Enclosure, right? Just look at this equality. Not an exterior, then it is an enclosure. And vice versa. So you can go in other direction. And now after that, look what is it. So it is not an interior. It means every neighborhood cannot be part of E. So intersection with complement is not empty, right? And also this point should be in closure, and it is written here. So once again, that is almost immediate. Okay, now next theorem contains main property which in fact explains the word topology. So theorem 3. Let me write just like 3 assertions. First, empty set and the matrix space X are open sets. Second, for arbitrary open sets, let me denote them G1, G2, the intersection G1 intersect with G2 is an open. And third, for arbitrary collection of open sets, G alpha are open. Their union is an open set. Proof. Okay, concerning empty set, we don't need to prove anything, right? It was mentioned before. And what is X? I can write X minus empty set and refer to that one, right? Theorem 2. So, complement to a closed set, we know it is closed, right? Also, empty set is closed. It was mentioned before. Closed, hence that is open. So that is about first. Second, look, take arbitrary point x naught in the intersection, right? Then x naught belongs to each of those sets, right? Because what means to be in intersection? Belongs to both sets simultaneously, right? Now, look. Those sets are open. And what it means? It means that for arbitrary epsilon greater, there exists epsilon I greater than 0, right? Such that neighborhoods with center at x0 and of radius epsilon I are in our sets Ji, I1, 2. So I wrote what means x0 is a point of an open set. Now you see, neighborhood with radius which is equal to minimum of epsilon 1 and epsilon 2 with center at x0. What it means? We consider all points such that distance from x0 is less than minimum, right? And if distance is less than minimum, then it's less than each of them, right? So it means that is a subset of, at least subset of, the intersection. Okay, I'll write like that. Right? In fact, it is equal, but it doesn't matter. And then, so, yeah. No, it's not good, not logical. Yeah. Yeah, then it belongs to the intersection, right? Because that one is a part of J1, but points of intersection, they belong also to that one, hence they are also in J2 as well, right? So they belong to both of them. So what it means? We found a neighborhood of x0 which is in our intersection. And concerning third, so if x0 take arbitrary point in the union, right? If it belongs to the union, then there exists an alpha, let's say alpha naught, such that x naught belongs to this G alpha naught, right? But G alpha naught is an open set. Hence, there exists epsilon such that epsilon neighborhood of x naught is a part of G alpha naught. But of course, one set is a subset of union of all those sets, right? And that's all. Yeah. No, union doesn't matter. That is very important difference. You see, for intersection of open sets, you can guarantee that intersection of open sets is open only for finitely many sets. I proved for 2, but of course you can repeat it finitely many times. Only finitely many times, right? But here, doesn't matter how many. That is why I put here A. Countable, uncountable, doesn't matter. Absolutely not important. You see, point belongs to union, hence it belongs to some of them, right? There exists an index such that it belongs to this set, right? The set is open, hence there exists a neighborhood which lies in this set. And a set always is a part of union of all those sets, right? That's it. That's very important difference between them. So here only you can extend it to finitely many, right? Intersection of finitely many. But not to infinitely many. And for union, you can do it for infinitely many. Of course, using duality, right? What we can write? Analogous definition for closed sets, right? But you need to change, right? So for closed sets, intersection of doesn't matter how many closed sets is again a closed set. But union, not. Union, not. Like here, look. This part. Every point, one point, is a closed set, right? And here we have union of infinitely many closed sets. That is not closed, right? As you could see from, where is it? Yeah. Closure of this set, in fact, is, look, so, yeah. You need, what is closure of this set? By the way, it's good to add here also about closure. It was not about boundary, right? But what is about closure? What is closure of this set? Closure is interior union with boundary, right? So you add to interior the boundary. And what is it? Closed intervals 1, 3, and 4, 5, and also 0.6. So union of infinitely many closed sets need not to be closed. And similar thing about intersection of infinitely many open sets. Okay. All points of closure are automatically adherent points. Yeah, these are adherent points. Only this, of course. What is closure? Closure is the sets of all adherent points. So these are adherent points. And you see, yeah, every point of the interval is adherent point because every neighborhood contains a point, right? And doesn't matter if that point belongs to our set or not, right? Rational or irrational. But also there is extra isolated point 6. Okay, by the way, maybe I should give a definition of limit point here. Okay, maybe after. Now, definition which explains this word topology, and let me give it now. So, definition. A set X is called a topological space. A topological space if there is a collection of subsets of X which are called open, such that the properties 1, 3 from theorem 3 are satisfied. And so look, I put open in quotes, right? Because okay, just a minute, there is a question why we used min neighborhood. Yeah, because why I used min? Because we need to a neighborhood, we need to find a neighborhood which is a subset of simultaneously both sets, J1 and J2, right? For each of them, we know there exists a neighborhood, right? But maybe they have different radii, right? And hence we need to choose minimal to be sure that it belongs to simultaneously both of them. Okay, and so let me return to this. And so you see, topology is in fact this collection of open sets. So somehow you define open sets. If those open sets satisfy conditions 1 to 3, then you have topological space. That's it. That is topology, nothing else. Okay. And you see, in metric space, you had numbers, right? Now, for topology, no numbers, nothing. Just those properties, nothing else, right? And in fact, it's enough to define limit. So let me define limit now, main definition, right, for us. So, definition. And I'll give the definition for the most general situation, firstly, for topological space, right? And then we go down to less and less abstract spaces. So, first, sequence Xn in a topological space X has a limit X naught in X if for arbitrary open set U which contains X naught, there exists a number such that for all n greater than this number, Xn are in this open set. So this open set is taken instead of neighborhood, right? So that is definition of the limit in a topological space. Now for metric space. For metric space, there is a difference. We take which open sets? Open balls. For metric space, we have distance. We have numbers. And we can consider epsilon neighborhoods. Okay, so sequence Xn in a metric space X. Oh, by the way, I forget to mention that every metric space is automatically topological space, right? Because of theorem 3. We proved it for arbitrary metric space, right? So it means automatically every metric space is a topological space. Has a limit X naught in X if for arbitrary epsilon greater than 0, now numbers appear, right? There exists capital N natural such that for all n greater than capital N, Xn belongs to epsilon neighborhood of X naught. You see the difference with epsilon added, or what is the same, right? Distance between X naught and Xn less than epsilon, right? So you see, now numbers appear. And also sequence Xn, let me put vectors now, in a normed linear space X. Okay, let it be E now, right? For linear space, I used E usually. Has a limit X naught in E if for arbitrary epsilon greater than 0, there exists capital N natural such that for all n greater than capital N, we have norm Xn minus X naught less than epsilon. So you see, we have three definitions, but they are the same. I mean, if you have a normed linear space, then, as we know, every normed linear space is automatically metric space, right? With metric given by this difference. So what is written here is precisely that distance, right? So it means that if you have normed linear space, then this definition coincides with all of definitions before, right? Yeah, and let me mention also one example which shows that sometimes it might be very strange, everything. I mean, you can refer to geometry, but it might be very strange, not coincide with intuition. So let me give an example of very strange topological space. So X contains two elements, A and B. Just two elements, nothing else. Open sets. Empty set. AB, it's for sure, right? Otherwise, first property is not satisfied. That is most trivial, right? Topology. But we can make a little bit more complicated. Just one point set A. Yeah? Okay. Let's check if it's true that that is indeed topological space. Look, these are open sets. First property is satisfied, right? Automatically. Second property, if you have intersection of any two, look, it's either empty or that one, right? If you have intersection of two different, right? If you have union, once again, it's among them, right? So all properties are satisfied. That is indeed a topological space. But now, what's about limit of sequences? Okay, let me consider such a sequence. Sequence is like that. A, and so on. So all xn are equals to A. Right? What is the limit of xn? Intuition says limit is A, right? That's true. Indeed. Look at the definition. So for arbitrary open set which contains A, we have two of them, right? Each of them contains, in fact, all members of our sequence, right? But that is also true. Why? Because look at the definition. We should consider arbitrary open set which contains our limit, right? Limit is B. Look at an open set which contains B. Only that one, right? That is the only open set which contains B. That one, right? Oh, of course, you can generalize it. Many generalizations, right? You see, so the only open set which contains B is that one, right? And it contains, again, all points of our sequence, right? So according to the definition, we have both equalities, right? So it means that for arbitrary topological space, you can define limit, no problem. But even uniqueness of limit may be not true. That's it. So that is why topological space, of course, very good thing, but you should to make extra conditions if you want to create something more or less suitable for applications, right? Because you see, even limit is not unique, so that is very strange. Okay, I have 5 minutes, and in fact, I should start new section now. What to do then? Maybe. Yeah, you see, in fact, I don't want to go deeper inside topological space anymore, but just to fix this property. You see, very bad thing if you have not non-uniqueness, right? There is a question. Does it mean A equals to B? No. No. Once again, what is written is valid for that sequence, right? Only in this topological space, with this topology. Crazy topology. That's it. Yeah. For normal topology, of course, that is not true. So that is what I wanted to say. You have no uniqueness of limit. That's it. And let me write down a property. So let me give definition. A topological space is called Hausdorff if topological space X for arbitrary AB in X A not equals to B, there exists two sets, open sets. U1 contains A, U2 contains B, UI are open, and U1 intersected with U2 is empty. So every neighborhood, every open set which contains a point is called neighborhood. I didn't want to write down the definition because usually I use words epsilon neighborhood, right? So just neighborhood with a ball with radius, right? But quite often is used also neighborhood without epsilon. What it means? Neighborhood without epsilon. It means arbitrary open set which contains our point. So maybe something else, right? Not only this. But for sure it includes epsilon neighborhood with some epsilon. And you see, Hausdorff space means that you can separate arbitrary 2 points. So you have two not intersected neighborhoods. And if you have Hausdorff topological space, then you have uniqueness of limit. So that's it. So that is why you can open many serious mathematical books and it starts with words. Let X be a Hausdorff topological space. So that's it. That is the most general situation where you can do analysis, I would say. Hausdorff topological space, because then you have uniqueness of limit and you can proceed further and further with further properties. Okay, I think I should stop now. And this example is an example of a topological space which is not Hausdorff, right? That's it. Okay, that's all for today.